PCl5. I think, didn't we cover? I mean, what you do is you look at how many groups. And so we just look at how many groups of electrons around. That's 1, 2, 3, 4, 5 groups of electrons. And then we can figure out the hybridization. The hybridization is you need an S, all 3 P's, and then 1 D. And so did I not draw this one? Did we draw it?
No, don't have it. No.
All right, sp3d is taking one of the S's, all 3 P's. So if we're looking at phosphorus, it's 3s, 3 P's. The next orbital is 4s here. And then we have the 3 D's here. And we would think we would hybridize the 3s to 3p and then 4s. But in terms of distance, you know, the 3, n equals 3 shells like this. But the n equals 4 shell, you know, is much farther out. And so it's harder to hybridize. So the 3s is in here, the 3 p's in here, and the 3 d's are in here. And so we end up skipping the 4s and going straight to the 3d. What we end up with is 5 equivalent orbitals. 1, 2, 3, 4, 5. Each of these are sp3d. However, they aren't totally equivalent because for phosphorus, we're going to have one orbital here. This is sp3d. And another one here. This looks like a p orbital, but this is not a p orbital. This is 2 separate orbitals. And we call these the axial orbitals. And then we have an equatorial here. So this will be sp3d equatorial. And then we have 2 more equatorials, one coming out here. And one going in here. So this is what you'd have to draw. This would be equatorial. And then we look how many electrons does phosphorus have. 1, 2, 3, 4, 5 electrons. Like this. 1, 2, 3, 4, 5 electrons. 1, 2, 3, 4, 5 electrons. And so we singly occupy each of the sp3d orbitals. And then we have to bond chlorine to that. And so it's kind of the same kind of deal. sp3d2 is similar, except it would be having an octahedral rather than a trigonal bipyramidal arrangement of orbital. This is the expanded octets. And for expanded octets, we need to take advantage of the d orbitals because to just do a regular octet, S and P is adequate. This gives us 8 in the octet. To get 10, we need 1 d. To get 12, we need another d. So we have the d2 configuration. Okay, other questions on this? Okay, let's go back. Take a look.
Yeah.
For the resonance structures, how many do you have to do? Or do you have to?
All of them.
All of them?
All of them for drawing Lewis structures, but for valence bond analysis, only one of them. So we wouldn't do it because they all look the same, so similar. All right, so what I want to do is finish up the brief. Yeah, the brief. You know, so basically 16 through 2 to 16.9 is reserved for Chem 1B. 16.10 and 16.11, the most advanced and most difficult stuff is thrown into Chem 1A for you. The reason why 16.10 and 16.11 now is because they deal with structure. So we're dealing with structure now. Let's talk about it here. And so what do you have? Why is HCl a strong acid but HF a weak one? For sure it should be, HF should be a weaker one. Why? HF should be a weaker acid because,
Bond strength.
bond strength, exactly. HCl, weaker bond, HF, stronger bond. But this is, if this were like HCl, HBr, it's easy, bond strength, But HF is a bit unusual because there's one other factor, because HF is like 1 trillion times weaker. But does it have 1 trillion times stronger bond? No, it doesn't. So why is HF unusually weak? Maybe that should be the question. But HF is an unusually weak one. Unusually because I'd expect HF to be a strong one, actually, because the bond strength, yeah, it's got a stronger bond, but still, expect it to be a strong acid. Turns out to be, HCl, HBr, HI, those are all strong acids, so HF should be there too. And it would, except for this. What was the issue, huh?
The polarity. Bond polarity.
It wasn't bond polarity. Because if it's bond polarity, HF should be stronger, because it's got a more polar bond. And so bond polarity would make HF stronger, but this makes it unusually weak. Unusually weak because of
Same thing.
The conjugate base is unstable.
the conjugate base is unstable for HF. HF is a much more reactive conjugate base. In fact, chloride, chloride is considered neutral. Chloride is not much of a base at all. Fluoride is a significant base, and so fluoride is unstable. But it's kind of related to that. It's not just the base alone, because there's something else that has to do with the stability.
Stability in water.
Stability in water we look at. In fact, fluoride turns out to be more stable in water than fluoride. You'd expect it to be. I would expect fluoride to be more stable. If fluoride's more stable, that should make HF a better acid, because the more stable the products, the more likely the reaction is. And so it's still not quite there yet. It's something else that only applies to HF, pretty much. Not HCl, HBr, HI.
Wasn't it because HF has a weak bond strength? That's why it's. Oh, no, never mind.
HCl is a weaker bond, so it's stronger. But
So it's a stronger acid.
yeah, HCl is a stronger acid. The weaker the bond, the stronger the acid.
So that's why HCl is stronger.
That's why HCl is stronger. And so that makes sense. HF should be weaker, but not unusually weak. What makes HF unusually weak?
Is it because it's fluorine's the most electronegative, so it's so polar? Like that fluorine doesn't want to give up the electron like that?
Well, it doesn't have to give up the electron, because HF, when HF loses a proton, fluorine gets to keep all the electrons. When HF loses the proton, fluorine gets to keep all the electrons. Not losing any electron.
Does it have to do with size?
It has to do with size and charge. I didn't talk about this at all?
I don't know. Tell me where I left off. Maybe I didn't get as far as I thought.
We talked about how HF is weaker than HI because weaker bond strength means stronger acid.
Mm-hmm.
And then we talked a little bit about bond polarity. And because HF is more polar, it's stronger than HI.
Yeah, so there's conflicting. Bond strength predicts HCl to be the stronger acid. Bond polarity predicts HF to be the stronger acid. That's fine. Those would be the observed trends. However, HF is even weaker than expected.
Because the distance between H and F are greater.
Because fluoride. Fluoride's a small ion, and so it's got a high negative charge density, which means, which means fluoride doesn't really break off completely. And so here, let's say water deprotonates HF, and so fluoride should go its own way, hydronium should go its own way, but fluoride doesn't give up. So there's kind of a tug of war for the proton between water and fluoride. The fluoride doesn't completely give up here and hangs on. This unit's called an ion pair. An ion pair is, it's not a bond really, it's just the fluoride just hangs on. And if the fluoride hangs on to hydronium, then hydronium can't react with other species. And so this inhibits the acidity of HF because the hydronium is not free to neutralize bases if fluoride's hanging on to it. And so what has to happen is another collision. Another collision has to break up the ion pair to free up the hydronium. Now the hydronium is free to neutralize bases. And so because of ion pair formation, this is not a factor in chloride, bromide, and iodide because chloride, bromide, and iodide are much larger ions. They're much larger. They aren't going to have this strong attraction to the hydronium. Once chloride breaks off, then it's free. Hydronium is free as well. So because of ion pairing. And so we know HF should be weaker because it has a stronger bond. Polarity contradicts this. Polarity says HF should be stronger because it's more polar, but we know that bond strength is most important. Okay, here the bond strengths are the same because they're both COH bonds. Both COH bonds, then we have to look at other factors because the hydrogen-oxygen bond being the same energy, we factor that out. And so we could look at polarity. We look at the polarity. The polarity looks the same, doesn't it? COH, the electronegativities. But is it the same? No. It's different. Well, how so? When we look at this is why we have to analyze it more detail. There's two ways, actually more than two, but there are these, but there are two ways that I showed you for these particular molecules. Okay? And so why? We're comparing acetic acid with ethanol. Let's take a look at the strength. Acetic acid is many, many orders of magnitude more powerful of an acid than ethanol. In fact, ethanol is such a weak acid, it will only react with the most powerful bases. And so most people treat ethanol as neutral. Those powerful bases that ethanol will react with aren't so exotic.
You know, I've used ethanol as an acid. I just reacted it with a very powerful base to pluck off the proton. So I was able to pluck off the proton on this. But you need, you know, you don't need nearly as strong of a base. You could use much weaker base for acetic acid, no problem. Pluck off that proton. And so why the difference? Well, it's not because of bond strength. It must be because of, yeah, it's the structure. It must be because, what were the 4 factors? You have this? Well, it's 4 plus factors because HF had that additional one. But, you know, that's rare, so we only considered that. Well, it's bond strength, bond polarity, stability as a conjugate base, stability in water. And so we looked at the next factor here. We already did this. This is just review. So what was your net conclusion? Why is acetic acid much orders of magnitude more powerful acid than ethanol?
The second carbon +3.
Yeah.
And then ethanol, the second carbon is -1.
All right. That's good. My analysis is like these 2 carbons are different. This carbon is a +3. +3. This carbon is a. What is this carbon again? -1. So these two carbons are totally different. One carbon is quite electron poor, the other is quite electron rich. And that's going to lead to differences in the polarity of the OH bond. In fact, which one's going to have the higher delta plus?
Acetic acid, sure.
Which one's going to be more proton-like? The top one or the bottom one?
Top.
Right. So this is a much bigger delta plus. So is bond strength being equal, then the hydroxide, like a base, a strong base like hydroxide, would definitely be more attractive to acetic acid than ethanol. And so a carbon like this is electron rich. It's pushing electron density into the OH group. This is electron poor. It's pulling electron density away. And so definitely a difference in polarity. Now, the book is going to show it like this. The book is going to show, rather than calculating the oxidation states, it shows arrows. And what did we call that? When we show arrows like this, we call that the what effect? So maybe the green arrows is showing the No, green arrow's not showing the pi bond. Green arrows are showing what? This is what I normally I don't do this review thing, but just to let you should be doing it though, and that is the information. This is like the scientific method. The information is just presented out there, and you go through and you organize it and you find the patterns, this kind of stuff. All that stuff is important in the scientific way of thinking. And so rather than me spelling out everything, I leave it kind of in some kind of like disarrayed state where I don't organize the conclusions for you. I want you to organize the conclusions for yourself. And so this is why it's disorganized in that sense. It's because these are just observations, and you take those observations and then you kind of put it together. And that putting together phase is so important, I think, in learning and better understanding the material. And so we're trying to understand this. I already went through all the answers for this. I just want you to formulate it yourself, you know? And I just went through, I didn't say, okay, this is the end result, this is the conclusion. You come up with a conclusion. And so the conclusion of this would be what? That, well, polarity is one factor, and the polarity is one factor, and the other factor would be back over here. Here we can see that acetic acid is like 1 trillion times stronger an acid than ethanol. 1 trillion times stronger. Well, one factor is the polarity. You know, how much more attractive is that proton? Is the proton 1 trillion times more attractive than this proton? Maybe. Are there other factors? Uh-huh.
Because ethanol doesn't mix in water?
Ethanol and water, actually, this is the next chapter. Next chapter. In the next chapter, we say ethanol is miscible in water. You know what miscible means? It mixes in all proportions. In fact, ethanol and water are a perfect match for each other. Close to a perfect match. Miscible liquids are good matches with each other. So is there any limit to how much water I can mix with water? Like if water and water mix? There's no limit. Ethanol's like that. Ethanol is like water, mixing water with water. You can mix as much water with water as you want. The same thing with ethanol. You can mix as much ethanol with water as you want. And so we call it infinitely soluble or miscible. And so interestingly enough, ethanol, even though it's got this big hydrocarbon, you know, it's not that big, so water molecules can break apart for this. When we go to butanol, butanol is insoluble in water. And you just add 2 more carbons to that chain and it becomes totally insoluble. I mean, we can dissolve barely any. If you get a pentanol, forget it. You know, pentanol, hexanol, forget trying to dissolve those in water because that chain's growing too big. You have to break up too many water molecules for that. Same thing with some of the acids. Acid chain length grows, becomes more like hydrocarbons and less like acid. Hydrocarbons and acid don't mix. And so what we also can look at is the stability of the conjugate base. And so let's take a look at that. These are the conjugate bases. So if ethanol loses a proton, we form ethoxide on it. And if acetic acid loses a proton, we form the acetate. And acetate has 2 resonance forms, which are shown here. And what's the difference between these 2 structures? You know, what stands out in terms of stability? What do you look for in the stability of the conjugate base? The what?
Localized charge.
Localized charge, right. Localized versus delocalized. So, the more localized the charge, the more stable. Is that correct? Or the more delocalized the charge, the more stable? Yeah. The more delocalized the charge, the more stable. And so here we see the negative charge. Is it localized or delocalized in ethoxide? It's localized. Over here, we see it's delocalized. In fact, the charge, the negative charge on each oxygen would be minus 1/2, which lowers the charge tremendously. And so what that means is this is a much more stable product than this. And so acetic acid is going to be a much better acid because, 1, its polarity is higher, and 2, acetate is much more stable, and that would be the conjugate base of the product than ethoxide. Ethoxide is considered a strong base. So ethoxide is about comparable in strength to hydroxide. Can you see? Hydroxide would be very localized, you know, all the negative charges on the oxygen. And so ethoxide's like that. It's very hydroxide-like. In fact, hydrogen and carbon have close to the same electron negativity. So you can see, if you just look in terms of electron negativity, if you look on in terms of oxidation state, then you know in hydroxide the oxidation state of hydrogen is +1. In ethoxide, the oxidation state of carbon is what? Here. So, you know what I'm asking? This is the question I'm going to ask you. What do you think is better, ethoxide or hydroxide? If you had to pick one, which one do you think is a stronger base? Hydroxide? Or the stronger base being the less stable. Just based on just the structure here, which one do you think?
Hydroxide.
Is more powerful, hydroxide or ethoxide? Hydroxide?
Which one's more powerful?
Yeah, which one is a more powerful base? Which one is less stable, more reactive? That's what I'm asking. Hydroxide or ethoxide? And why? We know we want to produce the more stable one in general, but you know, as far as stability goes, which one do you think? Here it's easy, you know. This is easy. Acetate's more stable. Ethoxide is less stable. Ethoxide should be a more powerful base, you know, conjugate base, more reactive, and higher energy in terms of potential energy.
It's stronger base.
Hydroxide is a stronger base than ethoxide? Why?
Because hydrogen is +1, and the carbon is +3. So basically means hydroxide could have stronger power to hydrogen.
So hydrogen is +1, and what? Oxygen is what?
Hydrogen is +1, so that means it has
All right. Well, if you do based on that, okay. Well, we just compare. We'll compare hydrogen is +1. What is oxygen? Or not oxygen. Oxygen is going to be -2, correct? But that's oxidation state. This is formal charge. In terms of formal charges, hydrogen's 0, oxygen's -1. In terms of formal charge here, carbon's 0, oxygen is -1. There's no difference, so it doesn't tell us anything. Right? However, the oxidation states do tell us something. What do the oxidation states tell us? The hydrogen is +1 and oxygen's -2. How about this one? What's carbon?
+3.
-3 and -1.
Yes. Yes. Here, not -1 though. Okay, 2, 4, 5. It's actually not sorry, it's not -3. What is it?
No, isn't the left one -3?
Oh, yeah, sorry, -3 for this one. But you know, this one that's one atom away is less significant because we got this atom here blocking it. It does play a role, you know, that the longer the chain. I don't know if I talked. Did I talk about this one here? I didn't talk about this one? Or did I? This one is -3. This is -2. But this one's different because this is -3 +1 +1 +1. This is -2, -2, -2, -2, -2, -3. As you look at this is what we call very electron rich. You know, hydrocarbons are electron rich. So which one is more electron rich? You know, is it the single one at -3, or is this long chain? -2, -2, -2, -2. Do all those -2s add up? And so if all those -2s add up, we get -2, -4, -6, -8, -10, -12, and then -3 is -15. So if I just add up all the negative charges, we get -15. Do they all add up? No, it turns out that, what does this say? Chain length has a little effect on acid strength. And so the chain length, that is, having this long chain of negative carbons here, doesn't impact it much. Well, the most impact is going to come off the first carbon here. And when we look at the first carbon, there's quite a bit of difference. This is -2, this is -3. This one's more electron rich. That's going to impact this. Well, this is the exact same question. You know what I'm doing? This is what I'm doing. I'm giving you this exact same question with 2 different species. Some people will say, hey, this exact same question as earlier. Some people go, wow, I've never seen anything like that, or done anything. If I talked about this before, if I haven't talked about it, it's fine. So, exact same question. Well, how would you know it's the exact same if you've seen it a bunch of times? Repetition. So I'm asking you the same thing. We analyzed it before, but I'm asking you to analyze it on 2 new species. Which one do you think is going to be a more powerful base? A lot of people will just say hydroxide because they've memorized hydroxide as a strong base. And that's it. But I would think ethoxide is more powerful, right? Why did you come up with that?
It's more electronegative because the second carbon's 0 and the hydrogen is +1, so the other would be
Well, what do you mean by more electronegative? Each atom has its own electronegativity.
more oxidation, it's more negative to the bond.
Okay, we don't call it electronegative. We call it something else. What is it? What is the negative charge on the carbon here? No, not 0. Well, anyway, I know it's been a while. Chapter 3's been a while. So, oxidation state is winner take all. And so, we have 3 different ways of counting electrons. 1, octet, total number surrounding. 2, formal charge, 50-50 split. 3, oxidation state, winner take all. Oxidation state, winner take all. We look at the difference in electronegativity. Carbon versus oxygen, who wins?
Oxygen.
Carbon versus hydrogen.
Carbon.
Carbon versus carbon. Well, carbon versus carbon's got to be
50-50.
Yeah, 5. And so carbon only ends up with a single electron. That's it, just 1 electron. How many electrons is it supposed to have? Oh, no, I'm wrong.
It should end up with 3.
Yeah. It's got more because it took from hydrogen. Winner take all. So it doesn't have 1. Fortunately, it's got more. It's got 1, 2, 3, 4, 5. Its charges -1. What you should do is you should draw these boxes. I stopped drawing these boxes because I just do it in my head. I just look at it and then can figure it out. That's the point you want to be. You just want to be able to look at it and just visualize it. Just say -1. That's where you should be. So it's -1, and then oxygen's -2. Now, to keep formal charge from getting mixed up with oxidation state, because they tell us 2 different things, right? We circle one and then put parentheses around the other. It's standard to circle formal charges. Let's just practice. You see, see that. Not always, though. Here, did they circle it? That's formal charge, but they didn't circle it because it's not always, but in practice, we should circle it. All right, now which one is a more powerful base? Now, what makes a good base? A good base is, a proton is positive or negative? Positive. So a good base is negative.
Negative.
Which one is more negative? Ethoxide or hydroxide? Ethoxide. Do you see?
Yeah.
Ethoxide should be a more powerful base. Why? Because this is what we call, an electron pusher. It's pushing electron. It's negative charge, so it's pushing electron density towards the oxygen. And so I'd expect ethoxide to be more powerful base than even hydroxide. And for sure, ethoxide should be a much more powerful base than acid. All right, that's the stability of the conjugate base. Then we look at the stability in water. The stability in water is how many water molecules do we break apart to make room. When we look at these two, structurally they're kind of comparable in size. And so as far as hydration goes, that is making these fit into water, there's not going to be much of a difference between the two. Both have a net -1 charge. When you add up the 2 minus half. And so not much of a difference. Here there is a difference, Here, if we look at these two, which one would you suspect to be a more powerful base? Well, we just look at the first carbon of this. Because all this is the same, the CO2 part of this. So we look at the first carbon here. What's the difference between the first carbon?
The bottom's a -2 and the top's a -3.
Yeah, this is -2, this is -3. So I'd expect this to be more powerful, less stable. I'd expect this to be less powerful, more stable. Not by much, because -2 versus -3, is there much of a difference? No, they're going to be very similar. And so if this one is more stable, then the acid should be stronger or weaker?
Weaker.
If the base is more stable, the acid should be.
Weaker.
Maybe I should do this. There's a seesaw relationship. The stronger the acid, the weaker the base. That is, the more stable the base is. The stronger the acid, the more stable. Like chloride. Chloride's very stable. And so this should be more stable, and therefore the acid should be stronger. This is the base. And so the acid is octanoic acid. Octanoic acid. But you look at it, and then we see, versus acetic acid, which one's stronger, octanoic acid or acetic acid? Acetic acid is slightly stronger. And so what this has to do is, yes, this should be more stable, but how much water do we have to break apart to fit this huge chain of carbon atoms? If I got rid of this, then if I got rid of this and put hydrogens on this carbon, this would be octane. Is octane very soluble in water? No, it's totally insoluble in water. So this is like oil. And so this is more oil-like than acid-like. This is much more acid-like. And so this isn't very stable in water. So this isn't very stable in water. That's going to mean that this, even though this base is less reactive, it's going to mean that this is less reactive acid. Does that make sense? It's not a huge effect, but it's something we got to consider. Now, there are other factors that play into this charge delocalization. Here, resonance delocalization is the most important. in organic chemistry, you learn a rule of thumb. The rule of thumb is the more resonance forms you can draw for a conjugate base like this, the more resonance forms you can draw, the more stable it is, less reactive. And so it's very simple. 3 resonance forms, more stable than 2. That's charge delocalization. But we can also look at other types of delocalization. Here, let's compare HOCl with HOBr. Here, again, the H bond here, the HO bond is the same in terms of energy. And so since they're the same in terms of energy, then we look at polarity. And so is there a difference in polarity? Yeah. There's going to be a difference in polarity because chlorine's electronegative is 3.0. Bromine is 2.8. Chlorine's more electronegative. So chlorine's more electronegative. So this will result in a bigger positive charge on the hydrogen, which means HOCl should be a stronger acid. And it is. If you look at it, HOCl, hypochlorous acid versus hypobromous acid. Hypochlorous acid is about 10 times stronger than hypobromous acid. Okay, now let's look at the, well, that was just polarity, but we should also look at the stability of the conjugate base and the stability in water. And so let's look at the 2 conjugate bases. If hypochlorous acid loses its proton, we form the hypochlorite ion, which is this. And the hypobromide ion for HOBr. Now here, both of these have localized charge, like hydroxide, right? But what do you think? Are these going to be equal in terms of strength compared to hydroxide? Do you expect them to be stronger than hydroxide or weaker than hydroxide? It's winner take all. So when we do oxidation states, there's no difference. If we look at formal charge, unfortunately, formal charge doesn't tell us anything, right? It's -1, 0, -1, 0. Unfortunately, oxidation state tells us nothing. Winner take all, so in this case, oxygen. -2, chlorine at +1. Oxygen at -2, bromine at +2. Actually, +2, sorry. +2, +2, -2, -2. So that's no difference in terms of oxidation state and formal charge. Are they the same strength? No, they aren't. Which one's stronger? And not only that, well, first, let's see. Just as a rough comparison, they're different in terms of strength, but as a rough comparison, compared to hydroxide, are these weaker, stronger, or about the same? Weaker. These are a lot weaker. Now, why are they weaker than hydroxide?
Chlorine's more electronegative.
Yes, chlorine. In this case, electronegativity works. Chlorine's more electronegative. And so what happens is there's going to be more of a tug of war here for electron. Oxygen's more electronegative than chlorine, but chlorine's more electronegative than bromine. And so chlorine's going to put a bigger fight. So chlorine's going to pull some of the charge density towards it. So this is called the inductive effect, right? As applied to here. The inductive effect as applied to here, actually it should be towards this, but this oxygen is already negative, and chlorine is losing electron density. And so chlorine's going to put up a bigger fight than bromine. And so if we look at the inductive effect here, chlorine's much more significant. And so if chlorine can withdraw some of the negative charge density towards it, that's going to it's not totally delocalized like
in acetate, but this is going to help delocalize the negative charge density on here compared to here. So here we expect more concentrated negative charge density than here. And so I would expect hypochlorite to be a weaker base, more stable than hypobromite. Because hypobromite is going to have more negative charge on the oxygen than hypochlorite. Which one is going to dissolve better in water? Hypochlorite or hypobromite? Which one is easier to dissolve in water? Hypochlorite. One, they're both the same charge, but hypochlorite's smaller, and therefore it's going to be better able to dissolve. And so that means hypochlorous acid should be a stronger acid on all three counts: polarity, stability of the conjugate base, and dissolving in water. Stability in water. So those are some of the concepts that we covered. And then we're going to have more applications as we go along. Like sulfuric acid versus sulfurous acid. Now, why do they show the structure like this? They're showing the structures like this is because they want to maintain the octet. There. So both of these structures have an octet, and so there's a little 8 electrons. And here, we could just use formal charge. You know, if you look at it, which one should be a more powerful acid? Well, first we look at the bond strength. Any difference in bond strength? The HO bond. No, they're both the hydrogen-oxygen bonds, sp3s sigma bonds. We got sp3s sigma bond there. No, not much difference. Should be the same. Then we look at what? Polarity. Which hydrogen is more positive? Which hydrogen is more proton-like? Proton being H+. The left one. You see that? Why is that? Yeah, the sulfur. If you look at the formal charge on the sulfur, +2 versus +1, +2 is going to suck more electron density from the oxygen, which is going to in turn suck more electron density from the hydrogen. That's one way. And so we could use formal charge to do it. But what if I wrote the structure like this? I mean, if I were to Google these, this is the structure of sulfuric acid off of Wikipedia. Well, look at Wikipedia, it has 2 double bonds, which means expanded octet. And if I go to sulfurous acid, let's take a look at sulfurous acid, which would be H2SO3. Sulfurous acid has this double bond here. See the structure? Actually, can we rotate this? No. But this was a rotatable structure. Okay. And so one way of writing Lewis structures is like that. The other way we could have written the Lewis structures is by expanding octet and getting rid of the formal charge. Well, let's get rid of the formal charge.
if I drew the structures like this, all the formal charges are 0. If all the formal charges are 0, now are the acids equal in strength? If I draw like this, the formal charges go down to 0, and the acids now should be equal in strength, because we argued earlier that because of the formal charge, the H2SO4 over here should be more acidic than the H2SO3. And so I just redrew the structure, so now are they the same strength? Because now the sulfur has the same formal charge. The sulfurs are both 0 in terms of formal charge. Are they the same now? All right, which one is a stronger acid? H2SO4? Why? Sulfur is more positive, both are 0.
You're still more cool in step one.
All right, so one way of explaining this is, we don't have to use formal charge to explain it. We could use the inductive effect. And remember the inductive effect is these oxygens, these are called terminal oxygens, suck electron density, which in turn suck electron density here. Electron density here. So we got 2 oxygens on that sulfur, terminal oxygens. Over here we only have 1, so it's going to result in a different positive charge on the hydrogen. That's the inductive effect. Here we don't have to use formal charge to do that. But does the inductive effect work so well here? If I drew it, does oxygen with a negative charge really want to suck electron density away, you think? It's got a negative charge. Yeah, for sure the sulfur does. The oxygen, well, in a way it does, because where did it get that extra electron? It took that extra electron from sulfur. And so there are different ways. We could use formal charge to explain the difference. We could use the inductive effect using these arrows, or we could use what to tell the difference between these two? So in terms of polarity, we're using the formal charge, like on this slide. We're using the inductive effect of these little green arrows, or we could use what? Think about it for a minute. What else can we use to show the difference in polarity?
Burned out.
Fluid is dissolvable in water. I don't know.
Just sort of.
Constant base.
Is that Google? Or Google Assistant? What's the question?
No.
Yes, sir. Yes, sir. You said yes.
A lot of little things. How's Eric been doing?
Huh?
How's chocolate?
I'm like, I'm more tired than I thought I was.
What do you mean? Oh, that better showing up.
I got home, took a shower, and I knocked out. I was watching a YouTube video, and then like.
Oh, did you get that job?
No, you just, they have all the kids track every so often
Mm.
at West. And he hated it. You haven't been going that.
Nope.
I mean, you don't need to.
Basically, yeah.
Are you gonna go back to our Are you doing anything?
Yeah, we'll do that.
Oh, so do you have it? What else can we use?
Oxidation state.
Oxidation state. So what are the differences in the oxidation states? What's the oxidation state on this sulfur?
Plus, Plus 4.
No.
2, 2, 2, 2.
Yeah, plus 6. How about this one? Plus 4.
Mm.
So that's better.
So here, with the oxidation state, you can see it, correct? Which one is going to have a greater positive charge? Well,
The left.
the left one. Yeah. Plus 6 is going to suck more electron density than plus 4. How about the oxidation states here? What's the oxidation state on this sulfur?
It's 2.
No, this should be circle. This is a formal charge. What's the oxidation state on this sulfur? Plus 6. The oxidation state on this sulfur? Plus 4. So we gotta use the oxidation state as well. So which structure is it? Is it that one or this one? Which structure is it? According to Wikipedia, it's this one. What's going on with these structures? So what we're going to do is we're going to look at H2SO3 right now. And what I want you to do is do a valence bond analysis on H2SO3. But which structure should we do? Well, we're going to do both structures. We're going to do this one with the single bond. And we're going to do the structure with the double bond. So why don't you go ahead and analyze those using valence bond theory and work on that.